Hello everyone. In this video we are going to look at classification using perceptron neural networks, and when I say perceptron here I'm talking about a single layer, although I show you a double layer too, but the learning rule we are going to use is single layer. When we have multiple layers, then we need to use backpropagation, which is a video that I'm going to make very soon. But so here is the simplest task. We want to classify some data using a basically hyperplane, which is a perceptron. Before that, I need to tell you one thing. So if you go to my channel under Deep Learning and TensorFlow, the new folder, I have my references, the three major references I have. So I just wanted to tell you. The one is Machine Learning Using TensorFlow Cookbook by A. Adewert and his colleagues, and that is an amazing textbook on TensorFlow. The other one is Neural Network Design by Dr. Hagen and his colleagues, and this is an unbelievably good book if you want to know about neural networks. When I was in grad school, I passed the neural network course with Dr. Hagen at OSU, and it was a pleasure and honor to be in his class. Extremely knowledgeable guy in neural networks, and he's one of the three people who wrote the neural networks toolbox for MATLAB so many years ago. That's an amazing textbook, very, very good to study on your own. And then the other one is Inside Deep Learning by E. Ruff. Okay, now that we know it, let's look at a single perceptron neural network. So here is a perceptron. So your input, which is a dimension of R, comes in, multiplied by the weights W, which has dimension of S times R, and added to the biases, constants that are dimension S by 1. So you get an output, which is S by 1, N, and then you pass this n to a hard limit function. And hard limit function is like a step function, which for negative numbers it gives 0, for positive or 0 numbers it gives a 1. And again, you might call it a unit step function. And so the activation, the output of the layer is the hard limit of inputs, okay, or the hard limit of W times P plus B, right? So this n, as I said, is what? This n that we have, the output right before going to the activation function, this n here, as you can see, is what? WP plus B. Okay, so we can use this, and clearly, you know, this is the equation of a hyperplane in general in any dimension, right? This guy here. If you draw it in the space defined by elements of P, that is a hyperplane. For instance, if P has only two elements, right, P1 and P2, then clearly this is a line. If P has three elements, then that is a plane, and anything above 3, which we cannot visualize, we call it a hyperplane. So let's say we want to use this simple neural network, right, for classification. And to demonstrate that, here I go with the AND function. And so P here, the vector P, has two elements, P1 and P2. So the output that I want to learn is P1 and then what? And P2. Well, we know the output is 1 only if both of them are 1, both of them are true. So at 1 and 1, you see here, the output is 1, but if any of these P1 or P2 is 0 on these three circles, the output is what? 0. So these are the 4 data that I have. For 3 of them, the output is 0. For 1 of them, the output is 1. So I have 4 samples, 3 of them belonging to one class, the other one belongs to another class. And I want to draw a line, a plane in general, in this case a line, to separate these two classes. One class is this and the other class is that. How do we separate these two classes of data? And when visually you can say that this line here would work, that's right. But a lot of other lines could work too. For instance, if you draw this line, that would also work. If you draw this line, that would also work. So any of them would be fine. And the goal of neural network here is not to find the optimal plane. If you want optimal plane, remember I have a video under machine learning called support vector machine, SVM. That will give you the optimal hyperplane. So here, as long as we find one hyperplane, one line, one plane that separates the two classes, that's good to go. That means we have trained the system. So the question is, this is a plane, and the equation for that is W times P plus B equals what? Equals 0, right? Where this P here is a vector of P1 and P2. So the question is, what W and what bias should I use to come with this hyperplane that properly separates the two classes of data? Okay, what? So what do we do here? So the single layer perceptron learning rule is you calculate error for each one of these data points. Remember, you have 4 data points. You calculate error by calculating the target, the value that you want to have, which are these numbers, right? At 0.00 it's 0, at 10 it's 0, at 01 is 0, at 11 is 1. So you calculate these t's from the output of the perceptron for that specific what? P1 and P2, right? So this A, remember this A is what? If you remember, it is hard limit of W times that PI plus what? B, where again that PI means one of these. Okay, so you do that and you'll get one error. Of course, these A's are all 2 by 1. These AI's, these TI's are all 2 by 1. So the errors that you will get also going to be what? 2 by 1. Okay? And then you multiply that error by what? By that P point itself, and add it to old weight to get the new weight. And you multiply this error just by 1 in this case, or you don't need to write 1. Just add that error to the old bias and you get what? The new bias. So if you keep repeating this recursive equations, ultimately, even if you start with a random W and with a random B, you don't need to know anything. You just start with some initial W and B, anything, a random would work. And these rules will guarantee that they change W and B such that all of these errors will converge to what? Will converge to 0. So this is called the perceptron learning rule, and it works perfectly for any sets of data which are linearly separable. What does that mean? Means with a single plane you can separate what? The two classes of data. For instance, if instead of this AND function I give you this set of data, right? Let's say at these 4 points you have one class, at those 4 points you want one class, and initially with a random W and a random B you draw a line like that. Well, clearly you see this line does not separate the two classes, right? Yeah. So now these update rules will change the slope and change the y-intercept until this guy turns, and finally come to something like this, which can easily what? Separate the two classes. And since here, as long as the error for all entries, for all samples go to 0, we stop the loop. We are not going to converge to the same result every time. If we repeat this experiment with a random W and a random B each time and keep going until the errors all converge to 0, one time we might get this hyperplane, the other time I might get this one time I might get this one. Okay, so as long as I can separate them properly, it's good to go. I'm not going to keep going until I get to anything optimal. So the final result, when you apply this perceptron learning rule, is going to be different each time. Now, let me show you how it is working with a simple code I wrote for you for animation, and I'm gonna put a download link on the video description for you to see that. So here is my code, and here is my AND function, as you can see. And you see I start my weight and I start my bias all random between 0 to 1. And I use this P1 and P2 here for drawing a line. Okay, so these are not a part of my learning or anything. These are just some data points, 20 data points I create, and then I define the function over them to draw the basically the separating plane. So these are all about the animation and everything. This is the learning rule. As you can see, I say as long as the norm of the error is bigger than some maximum error, which is very small, and as long as my maximum iteration is less than some the number of iterations is less than some maximum, keep going. Why should you use that? Because if you don't, and your network for any reason doesn't converge, now in this case it does, but in general, you always want to make sure that you don't stay in an infinite loop. Okay, in case your network doesn't converge, in case something is wrong. So you always want to stop after so many times, because this is very fast. This perceptron learning is extremely fast, and you really do not need several thousand iterations, or epochs you might call them, to converge. So you see I go over each and every one of the data points. I get that P1 and P2 form vector P multiplied by the error associated with that data point, and then add it to W to get new W, and then add that error to bias to get what? New bias. And then I update my plane, Y data, my X data of the hyperplane is the same all the time. My Y I will update. Then I use draw now to do the animation. And when for each and every one of these 4 points the error is updated, I go to the next iteration. So you see in each iteration or each epoch, I will update W and B from each and every one of the data points. Okay, so in iteration 1, when K is 1, I go over each and every one of these data points. I apply these formulas for them, and so W and B get changed 4 times. Then that is called one epoch. Then when I go to K equal 2, again I come back and use all 4 points for updating W and B, and then I go to K3, 4 until the hyperplane is properly separating the classes of data. Okay, so you see in each epoch you're going over each and every one of your data points in this case. Now, not always that's the case in neural networks, but here it is. And let me show you what happens. Okay, look. You see, strike, boom. Now it is, and by the way, in this case, it is passing right through a data, and it's fine because remember the hard limit function, for an input of 0, the output is 1. So although it's on the plane, still it is practically considered on one side of it, and because if it's bigger than or equal 0, the output is 0. So you see it is properly separating this single data point from these other 3. Now if you run it again, you're not going to get the same result. Look, you see, this time it's exactly on the side of these 2 data. It's not passing through any of them, and is perfectly separating. Is that optimal? No. If it's optimal, it has to be somewhere here in between this guy and the line connecting these 2. So again, it's just a result. It's not perfect, but that's what we want. We just want it to work, and it does. Okay, you see, there we go. This time here is closer to optimal, but in all of these cases the error for all 4 points is 0 regardless. So you see, this is working fine. Now if you want, you can go ahead and change this P and T to anything else that you want, and it should work as long as I said, the data are linearly separable. What does it mean? Well, look at this case here. In this case, clearly I cannot draw one line any way you can imagine to separate the black circles from the hollow circles. So the data in this case are not linearly separable. So in this case, regardless of what I do, there is no way I can separate them with a line. I need a circle here to separate them. And that's not what a normal perceptron does. We'll get to what we should do about it, okay? But that's not what we do in here. You can use a single support vector machine with kernels for this case, or you can modify these perceptrons. But perceptrons are for linearly separable data. So for instance, if I want to apply this, right? Let me just show you that. It's good to apply that. So let's say here, these corner points are 1 and negative, or yeah, that's fine. 1 and negative 1, right? So you have those. And again, this is also like 1 and negative 1, okay? If I have those, right, then could I write something for this one? Absolutely, yes. In this case, I have more data points. I have basically 8 data points, but let's go ahead and modify the code for that. Okay, so I added the data for this case here, right? And to make my code more general, because last time I manually asked the code to just add this P and this P and this P, draw a hollow circle, and this one draw a basically fill circle, right? But I don't want you to manually do that if you change your P and T data in this code. So what I did, I have a loop here for the plotting, and I said if the T for them is 0, if they are class 0, draw a hollow circle. If they are class 1, then fill it with red. So now whatever T and P that you plot in, it should work. Okay, it should work, and it does not need you to manually change anything. So I made the code a little bit better, more professional. So let's go ahead and run it. There we go. You see here, right? I'm doing this case here, and you see it is working perfectly fine. But as I told you, if you run that one more time, do not expect to get the same results, but expect it to converge. You see, this time it's almost touching this data, but again, it's working. So I would not call it perceptron learning, and I just call it what? Perceptron learning, and I call it single layer perceptron learning. Okay, so now it's completely appropriate. And one last thing I want to tell you is sometimes your data is like this. They are not linearly separable like the XOR function, the exclusive OR, right? So two data are here and here. For 0, 0 and 1 is 1. For 0, 1 or 1, 0 it's excuse me, for 0, 0 and 1, 1 it's 0. For 0, 1 or 1, 0 it's 1. Okay, so you have two classes, the square class versus circle class, and there is no way here you can separate them with a single line. But if you had two lines, like this and this, you could do it, right? So you can say as long as it's outside this line or outside this one, that's one class. If it's between these two lines, it's another class. So with a combination of two perceptrons, okay, you should be able to do that. And that's what you can do here with this multi-layer perceptron. So here you see I have two neurons, two perceptrons in the first layer. And I have a second one, okay? And what's the goal of the second one is to combine. So layer 1, neuron 1 provides one line, layer 1, neuron 2 provides another line, so this guy and this one, and then this one will combine them to get this. But learning that, the learning rule for this is not as simple as this guy here. Okay, if you have a multi-layer neural network, you need something called backpropagation, which is our lecture soon. We're going to talk about backpropagation, okay, which involves derivatives. And one of the problems we have with derivatives is these functions, these activation functions, they have to be differentiable. And the problem we have with the hard limit function is this guy is not differentiable. It's not a smooth function. So I'll show you later that instead of that, we can go ahead and use a what? I have it somewhere here. My notes are a little bit changed. But instead of that, use a sigmoid function. Okay, use a function like this. And this function is an approximation to this function, but it is a smooth function. So it is something like this. Okay, if n is the output right before the activation function, so your function is like this. And we're going to use that because this guy is differentiable, so, and backpropagation to allow the system to converge. And we'll go over that. So hopefully this video was useful to you. You get your first look at what is a perceptron neural network, a single layer, and how you can get it to work to classify linearly separable data with this demo. Feel free to change your training set and see that this guy will converge this animation. Thank you so much for your attention. I'll see you in the next video.